Alright, we're recording. Hello, my name is Andrew. If you are seeing this, then I wasn't able to partake in the whole session, and I apologize for that. Okay, let's start. Before I shall start this speech, I would love to share the sample sites right in the comment box of this video. Okay, either way, I don't really know where it's going to be presented. Either way. To start, I would love to start with an insight. I've been engaged in embedded programming for quite a while, and I noticed a specific growing trend. It has become literally not essential to read through and actually understand the datasheet or user manual before coding a specific chipset. Such trend is undoubtedly inevitable because there is because there is already a flurry of information on the net. However, this can only go so far, but I digress. The common consensus now mostly sees reading datasheets to be a somewhat outdated and even an unnecessary measure, and thus the collective proposition is just to, well, resort to simply using a prepared low-level code offered by an already downloaded IDE or IDE. This is, however, a huge error, as such code weighs too much and demands too much processing cycles, and would overall be non-compliant if your aim is to specifically develop quick and efficient code. Moreover, there is always the issue of the IDE just not supporting a given developmental board of your choice, or ultimately leaving you in a state of impasse. The solution to this conundrum is mildly simple. Read the datasheet and just write in register access code. Short and simple. This way you can, in average, depending of course on your microcontroller, get away with a spare of 50+% of cache space in the chipset. And with freeing so much space, you automatically unlock even more speed and potential. There is of course a caveat associated with this. Any given chip development company can all of a sudden just decide to, well, not supply a user manual or just not go into great detail in the datasheet, leaving the average end user to fend for himself and solely depend on the community for insight, which, to be honest, is not the most reliable source of knowledge. This is where I finally come in, or chime in. With my site, this site in particular, you must have a link for this site in the chat, in the comments section. Either way, with my site, I shall gather a myriad of microcontrollers as well as their collective datasheets and supply a simple and intuitive user experience for both neophytes and professionals alike in order to develop register access code. This way, the end user will not only be able to develop actually efficient code, but also learn the intricate details and workings of an arbitrary microcontroller and not depend on the pseudo-correct advices of random good Samaritans from Stack Overflow. Okay, now to the details. My site in general. Let's start over. As we see, this is the STM32F103C86 microcontroller, in short, the blue pill. Well, the name implies why it's called, its figure implies why it's called the blue pill. This micro, why? Okay, such question might arise. Why did I not use the Arduino board? Why did I straight go to the blue pill? Well, mainly because the blue pill is 4 times faster and 4 times more powerful than the Arduino. Why is there even a popular consensus to even use an Arduino? Use this. Either way, let's skim through what my site can do. As you see, this site can already generate register access code. As you see, we haven't chose any module yet, so this main loop is empty. So let's go through the functionality. We can go through the boot pins. These are the boot pins, but they are not that important. We can go through the physical pins. They are honestly also not that important. Let's go to the pin names. Here, these are the pin names. I'll remove the physical pin names, right, because they're not needed. For example, if we need to choose, for example, GPIO A pins, we go to any GPIO A pin. We scroll, and when we see that it highlights green, If you want GPIO B pins, we go to the B pins. Let's go to PB0. As we see, the timers and the I2C pins are also marked. We go here, it's highlighted. GPIO-C, we go here, it's highlighted. Let's choose, for example, PC13 or PC14. As we see, the pads are here. Let's turn them on. Inputs. These are both inputs. PC13 is input, as you see, is input. PC14 is input, as you see, is input. We can, for example, make PC14 to be output. As we see, it changed to output. PC13. Please remember, PC13 is input. PC14 is output. We can change the configuration, as you might remember. PC14 is output. It's at a mode of 50 megahertz. Bam. 2 megahertz. Bam. 10 megahertz. Bam. 50 megahertz. Its configuration: general purpose open drain, alternative function push pull, alternative function open drain, general purpose push pull. We can do the same with PC13 output here. Okay, and this is the side in general. Okay, I'll start with this.